Today, there's a great deal of secrecy surrounding the new American sixth-generation fighter, the Boeing F-47, and that level of silence is unusual even by U.S. military standards. Yet behind the classified details may lie the most radical transformation of the U.S. Air Force since the introduction of stealth technology itself. The F-47 is not simply intended to replace the aging Lockheed Martin F-22 Raptor fleet. Instead, it represents an entirely new philosophy of air warfare, one in which unmanned systems become full participants on the battlefield for the first time. The future battlefield envisioned by the United States relies on manned aircraft operating alongside swarms of autonomous drones. These combined forces will penetrate enemy air defenses, locate and destroy mobile targets, conduct electronic warfare, and maintain information superiority across enormous combat zones. At the center of this network will be the Boeing F-47, acting as the command hub that integrates reconnaissance, targeting, electronic warfare, and strike coordination into a single combat ecosystem capable of making decisions in seconds. This is not a conventional modernization program. It is a transition toward distributed air combat, where the vulnerability and enormous cost of a single super fighter are balanced by large numbers of cheaper but technologically advanced unmanned wingmen. In future conflicts, victory may depend less on individual aircraft performance and more on which side can manage its aerial ecosystem faster and more efficiently. In the 20th century, air superiority was largely determined by who shot down more enemy aircraft while losing fewer of their own. Today, however, warfare increasingly depends on the speed of detection, identification, decision-making, and strike execution. A nation may possess powerful missiles and advanced radars, but if it identifies targets too slowly or loses track of them at the critical moment, those advantages quickly disappear. Modern battlefields are saturated with layered radar systems, passive detection networks, mobile surface-to-air missile launchers, electronic warfare platforms, and vast numbers of inexpensive decoys. Under these conditions, survivability no longer belongs solely to the aircraft with the lowest radar cross-section. Instead, it belongs to the force capable of absorbing losses and continuing the mission without collapsing operationally. This shift explains why military planners increasingly discuss concepts such as distributed warfare and family of systems architectures within the Next Generation Air Dominance Program, commonly known as NGAD. Sensors, communications, and combat functions are now spread across multiple platforms, while critical data links are duplicated to ensure the network survives even after suffering enemy attacks. In future wars, fighters will no longer operate as isolated weapons platforms. Instead, they will serve as nodes in a larger network, linking intelligence gathering, electronic warfare, and lethal force into a unified and rapidly responsive system. America's adversaries are already adapting to this new environment. Modern air defense units frequently activate their radars for only a few seconds before relocating. Mobile missile launchers fire and immediately retreat. Cheap decoys force opponents to waste expensive precision-guided munitions. In such a battlefield, the side with the broadest situational awareness and fastest reaction time will hold the advantage. For this reason, the U.S. Air Force is placing unprecedented emphasis on data fusion, artificial intelligence, and automated battlefield management. Machines will increasingly handle routine combat decisions, while pilots supervise operations and retain authority over the use of lethal force. This is where unmanned wingmen become essential. No longer simple support drones, these systems are evolving into fully capable combat assets. They can function as remote sensors, communication relays, jammers, decoys, or additional missile carriers. If drones become the muscles of future air warfare, the F-47 is intended to become the brain and nervous system coordinating the entire force. The aircraft's designation itself appears symbolic. The 47 likely references several historical themes simultaneously. It recalls the famous Republic P-47 Thunderbolt, later redesignated as the F-47 after the U.S. military changed aircraft naming conventions. It also references 1947, the year the independent United States Air Force was officially established. Finally, many observers believe the number also references the 47th President of the United States, Donald Trump. The Boeing F-47 is expected to become the centerpiece of the broader NGAD initiative, replacing the Lockheed Martin F-22 Raptor with a family of interconnected systems centered around a long-range stealth fighter previously associated with the penetrating counter-air concept. Although most design details remain classified, one rendering released in 2025 attracted particular attention because it appeared to show forward canards, or horizontal stabilizers, near the front of the aircraft. This was unexpected because canards are traditionally considered problematic for stealth aircraft due to their radar reflections. However, canards also provide important aerodynamic advantages. They improve maneuverability, increase stability at high angles of attack, and enhance control authority for tailless or delta-wing aircraft. Their inclusion may indicate that Boeing prioritized agility and flight performance despite the stealth trade-offs. This debate is not entirely new. China's Chengdu J-20 has often been criticized for using canards while still claiming stealth capabilities. Yet historically, even American stealth fighter concepts, including early programs connected to the Lockheed Martin F-35 Lightning II and the original advanced tactical fighter competition that produced the F-22, experimented with similar aerodynamic layouts. As a result, some analysts believe the public renderings may intentionally contain misleading design features to confuse foreign intelligence agencies. Others speculate that the F-47 could appear in multiple configurations optimized for different operational theaters, such as the Pacific or Europe. Another major concept associated with NGAD is Open Mission Systems architecture. This approach allows rapid integration of new sensors, weapons, software packages, and mission modules without requiring the entire aircraft to be redesigned. In many ways, the fighter becomes comparable to a smartphone. Its capabilities evolve continuously through upgrades rather than remaining fixed at the moment of production. This modularity is partly driven by necessity. Advances in artificial intelligence, cyber warfare, and electronic warfare now occur much faster than traditional military procurement cycles. The Air Force can no longer afford to wait decades between major upgrades. Powering the F-47 will likely be an advanced adaptive cycle engine developed under the next-generation adaptive propulsion program. Competing designs from General Electric and Pratt & Whitney, known as the XA-102 and XA-103, are expected to provide dramatically improved fuel efficiency, speed, and thermal management. These engines could allow the fighter to switch between efficient long-range cruising and high-speed combat performance exceeding Mach 2. Some analysts even speculate that future variants may incorporate hybrid electric technologies for quieter operation during specific mission phases. According to Air Force leadership, the F-47 may achieve a combat radius exceeding 1,000 nautical miles, a critical requirement for potential operations across the vast Pacific theater. Stealth technology will also extend beyond shape alone. Reports suggest the aircraft may utilize advanced metamaterials and adaptive thermal coatings capable of managing heat signatures and radar reflections more effectively than previous generations of stealth aircraft. The fighter's onboard information system may become one of its most revolutionary features. Instead of forcing pilots to manually interpret dozens of instruments and sensor feeds, the aircraft's AI will combine radar data, passive sensors, optical systems, satellites, and friendly aircraft information into a single verified combat picture. Targets will automatically be prioritized according to threat level, while the system recommends tactical responses in real time. In effect, the F-47 could function as a flying data center capable of processing information faster than human operators alone. Naturally, even the most advanced fighter still requires powerful weapons. The primary long-range air-to-air weapon associated with the F-47 is expected to be the AIM-260 Joint Advanced Tactical Missile, designed as a successor or supplement to the AIM-120 AMRAAM. Reports suggest the missile could exceed Mach 5 and engage targets at ranges beyond 120 miles. However, NGAD doctrine increasingly emphasizes off-board weapons. Instead of carrying every missile internally, the F-47 may direct weapons carried by collaborative combat aircraft, or CCA drones. This preserves stealth while dramatically increasing available firepower. Future compatibility with hypersonic weapons and even directed energy systems is also being considered. Although fighter-mounted combat lasers still sound futuristic, the aircraft's modular architecture is reportedly designed to support entirely new weapon classes without requiring a complete redesign. The CCA concept itself involves an entire family of drones serving multiple battlefield roles. Some will function primarily as reconnaissance platforms, others as electronic warfare systems, missile carriers, or decoys. Their autonomy levels may vary significantly depending on mission requirements. In a typical operation, an F-47 might control several CCAs simultaneously while remaining at a safer distance from enemy air defenses. Some drones would use passive sensors to identify threats, others would jam enemy radars, while strike drones launch missiles based on targeting data supplied by the network. If enemy air defenses activate their radars, decoy drones could intentionally expose themselves to trigger enemy responses. Once those radars reveal their positions, strike drones immediately launch attacks, often without requiring the F-47 itself to illuminate the target. This radically changes the economics of air warfare. Losing a few unmanned systems becomes acceptable if it protects a highly valuable manned aircraft and ensures mission success. Nevertheless, the challenge of autonomy remains enormous. Artificial intelligence systems must reliably distinguish real targets from decoys, resist electronic deception, and function under extreme combat conditions. For this reason, human pilots are still expected to retain final authority over lethal decisions. So far, the U.S. Air Force has identified two prototype collaborative combat aircraft: the YFQ-42A developed by General Atomics and the YFQ-44 developed by Anduril Industries. Current plans reportedly envision a future force of approximately 185 F-47 fighters supported by at least 500 collaborative combat aircraft, with long-term ambitions potentially expanding far beyond those numbers. If the United States successfully matures this ecosystem, the F-47 will become far more than just another stealth fighter. It could emerge as the centerpiece of a new era of warfare where information dominance, automation, and networked combat determine victory faster than traditional dogfighting ever could. In future conflicts, the most valuable resource may no longer be missiles, fuel, or even stealth itself. It may simply be time, the ability to detect, decide, and strike before the enemy can react.